take as much time for us to get started? Sorry. Thanks. All right. Hello, everyone. Welcome back to Theorem. It's our first one of the semester. Hope you guys all had a nice holiday. Before we get started, I'd like to point out that we're still looking for speakers. So if you or anyone you know would like to give a talk, please contact either me or Nama. My name is Nicholas. And all right, without any further ado, I'll introduce our first speaker, who is Amir. He is a second-year PhD student advised by Bernard Heupler, and he will be telling us about synchronization strings and things related to insertion and deletion coding. Okay. Thank you.
Thanks. Okay, I'm going to talk about synchronization strings today, which are very, very simple mathematical objects that surprisingly can be helpful when it comes to communication problems that in which we are dealing with insertion deletion errors. But before getting to the synchronization strings, I would like to start with a little bit of an overview over some simpler notions and definitions in coding problems in general. Well, imagine this situation that we have two parties which we'll refer to as Alice and Bob. And one of them has some data, some information that she wants to send to Bob. And any of these pieces of information are a member of some set sigma, which we'll refer to as alphabet. And let's say we have some sort of channel or medium of communication between these two, that Alice has to use this medium of communication to convey its messages, but there is some bad guy on the channel who is tampering with the messages that are being conveyed. In particular, we assume that this guy, who we refer to as adversary, can change up to p fraction of messages that are being sent through this channel. So what Bob receives is not exactly what Alice sends. And having such a setting, we are looking for solutions to convey as many bits of information as we can from Alice to Bob. Now, one natural solution to this problem are error correcting codes. An error correcting code is simply a subset of this set sigma to the n. As I told you, we refer to sigma as alphabet and to n as block length. Now, well, as you all might have probably seen, you can think of a huge graph with sigma to the n number of vertices, where any vertex in this graph corresponds to some string of length n over alphabet sigma. And I connect two of these vertices if the corresponding strings are only different in exactly one position. Now, this set C is a subset of sigma to the n. If we have this nice property that any two members of C are far enough from each other, or in other words, the number of positions that any two members of this set, the number of positions that any two members of this set are different in is greater than delta times n, where delta is some constant between 0 and 1, we can actually correct delta n over too many errors. I mean, if adversary is guaranteed to inject less than, or like change less than delta n over too many symbols, Bob can always understand what Alice was supposed to say. And I guess you can see why. Because Alice is always going to send one of the members of C, which is of these red dots here. And what Bob receives is going to be like at most delta n over 2 far from this red dot, which means it's going to be in this ball of radius delta n over 2. And these balls are like mutually exclusive, so Bob can uniquely decode or find out what was the string that Alice tried to send. Another important definition for error correcting codes is rate. So let's say we have an error correcting code C, and we are using this to communicate, to send information from Alice to Bob. What Alice actually does is determining one out of size of C many choices, and like sending this to Bob. This looks like sending log of size C many bits of information. while potentially he could send n many symbols out of set sigma, which is like having a potential of sending n times log sigma many bits of information. So rate is a notion which shows how efficient your error correcting code is. Yeah.
If delta is 1, then it means that Bob can understand even if half the message has been destroyed.
Yes, that's true. But if delta is 1, size of the set C cannot be larger than 2. The second string has to be like exactly the complement of the first one. And one of our very, very important concerns here is the complexity of encoding and decoding, which is if Alice like has a number between 1 to C, how fast can she find the string in sigma to the n which corresponds to that, or the string in C which corresponds to that number. And on the other side, when Bob receives one of those dots here in one of the circles, how long does it take for him to determine which dot is in its close neighbor? So, this is probably the last thing that I'm going to say about error correcting codes, and it's a very simple observation, which says size of C should be smaller than this thing. Can anyone see why? Okay. All the members of C are supposed to be n times delta far apart from each other. So if you conceal n delta minus 1 first symbols of members of C, what remains should be a set of distinct strings. None of those two strings can be similar. So the size of C cannot be larger than this thing. And doing some simple math, this results to a very important inequality which we will refer to as the singleton map. This kind of shows the natural trade-off that we expect to be between distance and rate. I mean, if you want a code with very, very large distances, you are not going to have a good rate. You are going to have a small set C. On the other hand, if you want a large set C, you cannot have like super large distances. So delta plus R should be bounded by something. That thing is 1. So okay, before moving on, is there any questions from this slide? Yeah.
So little r is the rate?
Yes.
Okay.
Yep. So the communication problems in which the error type is insertion, deletion is basically the same kind of problem. But instead of changing symbols, we assume that adversary can like insert or delete some symbols into within the communication. As a very simple example, let's say we have an alphabet of size 3, A, B, C, and n rounds of n equals to 5 rounds of communication. And this guy is allowed to have like 40% of insertions and deletions, which here would be like 2. A simple example would be like this. Let's say Alice sends A, and A goes through, Bob receives B. A. Then Alice sends B, adversary decides to delete B. Then Alice sends A, he lets the A pass away. So on and so forth. So one thing that I'd like to note here is, as you can see, these two strings are not necessarily close by concerning, if you like look at their distance under Hamming distance. Because one single insertion can like shift the whole thing one unit forward. So naturally and intrinsically, we expect insertion deletions to be harder kind of tampering with the message. So designing solutions for communication problems that are suffering from insertion deletions would be a harder job. Okay, now I'm going to define a distance which is going to be helpful when it comes to insertions and deletions, and that's edit distance. Edit distance between two strings is the minimum number of insertions and deletions you have to make in order to turn A into B. Like as a quick, simple. Can anyone say what's the edit distance here? Yeah, you should remove A and then insert B. And it's kind of clear that edit distance is a distance, because edit distance of any string to itself is 0. The distance of A and B is equal to the distance of B and A, because you can just insert anything that you've removed and remove anything that you've inserted. And transitivity is also kind of clear. So let's move on. Now that we have this notion of edit distance for different strings that might end up appearing on the Bob side, you can think of insertion deletion codes very, very similar to error correcting codes. Like we have some sort of distance here, so you're looking for a large subset of sigma to the n, whose members are far apart, but this time under this new kind of distance. Okay. What we are going to try today is trying to find solutions, basically trying to find good insertion deletion codes. Let's consider a very simple case. Let's say your alphabet size is very, very large. It's so large that you can actually attach the index of the message that you're sending to each symbol which is being sent through the channel. So you attach 1 to M1, 2 to M2, so on and so forth. So what Bob really wants to do here is try to find out the actual index of the messages that he receives. But there are a couple of cases that can happen here. One of them is that Bob, well, for some index, let's say index 1, Bob receives only one symbol with index with that number. So in this case, he can kind of be sure that this was what Alice meant to send. The other things that happen is that, like, he don't receive anything with some particular index on. This is what happens here for the index number 2. So he doesn't know what the second message is. For index number 3, he has received 2 different messages. One of them was genuinely sent by Alice. The other one was inserted by the adversary. So here he cannot decide whether the third message that Alice sent was M sub 3 or M prime. Here he still has some kind of ambiguity. So let's put a quick question mark here. There is also another case where adversary deletes some particular index but inserts a phony message with the same index number. In that case, Bob assumes that the 4th message was M double prime, while it was not. So what happened here is, if we have the ability to attach these large indexes to any of the messages that we send, Bob is actually able to kind of construct a new vector here, which is equal to what Alice was supposed to send, except that some of the positions may turn into a question mark, and some others may turn to some wrong message or corrupted message. So I'm going to introduce a new type of errors, which I'm going to refer to as half errors. I say that this message is corrupted by k half errors if adversary have changed some of the messages into question marks and have changed some of them to a totally different thing, such that if you count the number of question marks plus twice the number of messages that has been changed, that number is smaller than k. or that number is actually the number of half errors. You can think of it as some sort of budget. Let's say adversary has a budget of k half errors. You can spend any of those half errors changing one symbol into a question mark or one question mark into a problem. So what this procedure does here is actually turning k insertion deletions into k half errors. A very important thing is that half errors are way, way easier than insertion deletion errors to be, to be dealt with. In particular, if you have a good regular error correcting code, which has a distance of delta, I mean, the Hamming distance between its members are like larger than delta n, its half error distance is also going to be large. I mean, 2 delta n, because half error, well, let's say you have 2 strings. The number of symbol changes that you need to reach from the second, reach to the second one from the first one is exactly equal to half of the number of half errors you'll need to do this sort of conversion.
Sorry, what was your definition for half error?
Half error is so if adversary has like k half errors, you can spend each of them to turn one position into a question mark, or a position which has already been turned into a question mark to another symbol. So it's kind of a relaxation of Hamming distance.
I'm sorry, then do you mean like the k erasures?
Pardon me?
The erasures?
Erasures are also a special case of half errors.
So you can either flip the bit or erase it?
Yeah, but flipping counts like twice. It's like first erase it and then replace the question mark with some other message.
So this is for the index, but you can also change the message and so on.
Changing counts as twice, which is equivalent to like first changing.
It doesn't matter, like index.
Yeah, it doesn't matter.
So if you think about it as a disk, like you can write new stuff, but you have to delete what's there. So writing counts twice, while deleting only counts once.
Exactly. Well, let's say you want to, like, here's a simple example. If you want to turn the first one to a second one, you have to do like 2 symbol switchings. And equivalently, you can do like 4 half errors. Okay. The most important point in this slide is that regular error correcting codes that have distance d are also good codes against half errors and have the distance of 2d. So you can actually, in the previous slide, what we did was like changing k insertion deletion errors into k half errors. Now, what's left here to do in order to get good insertion deletion codes is just finding good half error codes and apply them to the message that Alice is sending, which is M. That's what we're going to do. This is what I just said. If you have a half error code which has a rate r and a distance delta, and you have a very large alphabet that allows you to do such a thing, you can easily turn it into an insertion deletion code with a slightly smaller rate and a distance delta. So is it clear?
The extra logo is just the index, right?
Yes, exactly. And as I mentioned before, the downside is that this method requires the size of sigma being like omega of log n, which is too large. We are particularly interested in finding error correcting codes over alphabets whose size are like constant in n. So the big question is that, can I replace that string of 1, 2, 3 till n with some other string whose alphabet size is constant in terms of n and enables me to translate k insertion deletions into k times 1 plus epsilon half-hours. I mean, I relaxed this condition a little bit in order to get constant size strings that can play the role of like synchronization or finding the indexes or turning the insertion deletions into half-hours. And what I'm going to talk about today is the answer of this question, which is yes. And we're going to introduce some strings that we'll refer to as synchronization strings. And they have this property. And as a fun fact, their alphabet size is not only constant in n, but is also only polynomially large in terms of epsilon. Okay, before getting to the synchronization strings themselves, I'm just going to state the formal theorem that they imply. If you have a half-hour code C, which has like rate r, distance delta, alphabet of size, this is the bit size, so it would be like log of size, and some encoding and decoding complexity, you can use those strings, those synchronization strings, as a black box to turn them into insertion deletion codes by adding a linear time to the encoding complexity, a n squared time to the decoding complexity, and just losing a small amount of rate. And so if you use this famous error correcting code, which was introduced in the work by Venkat and Piotr Indik in 2005, this implies that you can have insertion deletion codes with distance delta and rate 1 minus delta minus epsilon for any delta and epsilon with linear encoding complexity and n squared encoding complexity. This kind of means you can achieve as close as you want to the singleton map. While the best previously known error could achieve like 1 minus of the square root of delta. So it's not only a order of magnitude improvement over that result, but the fact that this constant factor here is 1 kind of closes the gap, shows that, I mean, it nearly closes the gap because of this epsilon. But, I mean, you cannot hope for a like significant improvement here anymore. Okay, let's get to the definition of synchronization strings. As I mentioned before, these objects are very, very simple objects. We call a string S over some alphabet sigma an alpha synchronization string if it has this property. For any three distinct indices I, j, and k, consider the substring that includes indices from I to j minus 1, and the other one indices from j to k minus 1. S is an alpha synchronization string if the edit distance of these two substrings is larger than some constant factor of the overall length of this interval. So this is a very simple definition. I'm going to show that if a string has this property, it can be used as a good candidate for the problem that we saw in the previous slide. And also I'm going to show after that that these kind of strings can be constructed pretty fast, efficiently.
Sorry, what's ED stand for?
Pardon me?
What's ED stand?
Edit distance. Yep. So there is this property that can be like easily implied by the definition of alpha synchronization strings that all such strings should have. Let's say S is an alpha synchronization string. Now, consider a matching between the members of S and itself, which is a monotone matching. And by monotone, I mean its edges do not cross. And also, if you look at the particular edge, the indices of its two ends cannot be identical. I mean, one of the ends should be strictly like larger than the other one. this, if S is an alpha synchronization string, it has the property of such a matching is smaller than 1 minus alpha times n. Now, it intuitively shows why these sort of strings would be good for dealing with insertion deletions. Well, let's say Bob is looking for, Alex is sending S, and Bob is looking for some particular substring of this string, which is large enough, which is larger than 1 minus alpha times n. What this theorem says is Bob cannot be fooled about all of the positions that he's looking for. Well, he's looking for some sort of substring here, and he may find some other substring here. But if the length is large enough, at least one of the positions has to be correct. Has to be correctly decoded. If you didn't get it, it's not important. Okay. So let's see how. So if you get back to the. Okay. What I have to show here is that how Bob can use this string to translate those insertion deletions into half-hours. In order to do so, what he has to do is, for any symbol that he receives, he either matches it to some of the symbols that he was expecting to receive, or ignores it. Like detects that is a symbol which has been inserted by the adversary, so I'm going to ignore that. The algorithm is pretty easy. What we do is just finding the largest common substring between those two strings. Now, here the red lines show the largest common substring in these two strings, and blue lines. And the dashed red lines show the actual string. I mean, the matching which corresponds to what adversary has actually done. Of course, there can be some wrong decodings here, but what I'm claiming is that the number of these wrong decodings is not going to be too large. What's the reason? So let's say you have, for some index, you have a wrong decoding. What happens here is this index has an actual match on the other side, which was, what it was actually supposed to be, and one mistakenly decoded mate on the other side. So those two indices here has to be equal. I4 and I5 has to be similar symbols. So you basically have two positions here which are like identical. If you have too many mistakenly decoded indices on the right-hand side, you are going to have too many of these pairs on the left-hand side. And this contradicts the self-matching property that I just talked about. Because if you have too many of these pairs, it's like having a very large matching from the left-hand side string to itself. And as left-hand side string is a alpha synchronization string, that's not going to happen. So the algorithm actually, it's not the only thing that we do. We first find the large LCS between two sides, then remove everything which has been matched on the right-hand side and repeat the same thing. Do this like 1 over 1 minus square root of 1 minus alpha times. And then at the end of this process, Bob again tries to build this table, and the way he does it is kind of clear. If for some index on the left-hand side you have only one match on the right-hand side, that's going to be what you decode the first message to be. And if you have more than one or no edges matches to it, you're going to return the question mark. So I'm not going to prove this today, but it can be seen that NP insertion deletions, or k number of insertion deletions can be translated into k times 1 plus this thing, many half errors. And this can be done, so we have this many LCSs, and each of them are going to take like n squared time. So the complexity, the extra complexity for turning these indels into half errors would be this thing. And this square root of 1 minus alpha is actually that epsilon that I was talking about. So as you can take alpha as close as you wish to 1, you can make this thing as close as you wish to 0. So what I have just said is that you can turn k insertion deletions into k times 1 plus epsilon half errors in a quadratic length time.
Okay, so this might be a silly question, but so the way that I understand it, this is in that same adversarial setting. So Bob only sees the right-hand side. Right? It's like he doesn't actually know what Alice's original string. So what exactly
no,
are you
this
comparing?
string is agreed upon before the. So this I1 to In is the synchronization string, which is known to both sides.
But that's like the communication protocol in like the
Yeah.
of
But they are all attached to some messages which I've removed. I mean, each ij is attached to some mj, which is the message that is coming. So ijs are only used for the purpose of indexing,
Right.
like building up this table. Okay. So now I'm gonna talk about the existence and construction of these sort of strings. So let's say you have a random string with like n different elements, each of them being randomly chosen from a set of size q. What I'm going to say is that there is a non-zero probability that this string is a good synchronization string. And this is the way that I'm going to show the existence of synchronization strings. I'm going to define a bunch of bad events, a sub ijk, where, as you can guess, is the event in which the substrings I, j, and jk do not have the property that we wished, we needed a alpha synchronization string to have. And what we do here is using Lovash's local lemma to show that for a large enough Q, with a non-zero probability, none of these bad events happen. There's a little bit of a technicality here. This can be shown for, you can show that these bad events do not happen for bad events that are large enough. Where k minus I is large enough. Because for very small intervals, the probability of being bad is too large. And what we do after, so far we have found like a string which has the desired property, but just for long string, like long substrings. What we can do, we can like concatenate each symbol of this string with another string which is simply 1 to t, 1 to t, 1 to t repeated. And this second part is going to take care of like small bad events. The first part is going to take care of large bad events, and it's going to be a good alpha synchronization string. Well, this basically shows that alpha synchronization strings do exist over alphabets whose size is like polynomially large in 1 over 1 minus alpha. Remember that this used to be our epsilon, so the alphabet size is like polynomially 1 over epsilon as a promise. And well, you can use this famous paper of Moser and Tardush to show that you can actually find the good, desired values of R1 to Rn in a polynomially long time. So, okay, from now on, I'm going to start talking about another useful aspect of synchronization strings. So, if you weren't following me, it's a good time to like reboot. And I promise to like be more clear. Well, I'm going to define a new distance notion right now, which I'm going to refer to as relative suffix distance. The suffix distance of two strings s and s prime is defined as follows. Look at the suffixes of length L of both strings, and look at the relative edit distance of them. I mean, by relative edit distance, I mean edit distance over the length of them, and then maximize it over L. This would be the relative suffix distance. One very, very useful property that synchronization strings have is that if you look at the set of prefixes of synchronization strings, any two prefixes are going to be far apart by at least alpha under the notion of suffix distance. Yeah.
So here, does SL and SL prime must be the same index, or they're just like two strings with length L?
S and S prime are two different strings, but
Should they be like exactly the same index, or they can be?
yes, they should be exactly the same length. I mean, well, you've probably, well, there is another pseudo distance which is similar to this one, where L and L should, I mean, the two suffixes are not necessarily of same length, which gives a better result, but I'm just keeping it simple. Okay. Now, let's say what we want to do here is that this time we want Bob to decode the index of this symbol he receives right at the moment he receives it. So in the previous one, we waited for the whole thing to come in and then ran an algorithm to find what the indices are. Let's say Alice, let's look at the communication at some point of it being wrong. Let's say Alice has sent like the first K messages. It's gone through the channel and has been altered a little bit by the adversary, and Bob has received this thing. The only thing that Bob actually needs to know is the value of K, is where Alice is. I mean, how far she has gone through the message that she's supposed to send. So he has to decide which of these prefixes has been sent so far. The property I talked about in the last page was all of these prefixes are actually far apart under some sort of distance. So a natural way of deciding between where Alice is just finding the one here which has the closest distance to what Bob has received under that suffix distance. And it can be shown that using this algorithm, you are going to find out the distance correctly most of the time. And that way, if you have like K many insertion deletions being applied here, on the other end, you can guess the indices correctly most of the time. In fact, you are going to have at most 5K times this thing half errors. And this O of 1 is something in terms of alpha, which goes to 0 as alpha goes to 1. Yeah.
Is that 5 necessary in the previous thing? It seems. I don't
Not really. I mean,
is that
just the
sort of
constant.
like the best you can
I mean,
get, but do you think that's actually?
It used to be 1 in the previous, and that was something important. But
Yeah.
whenever it's something more than 1, I mean, it doesn't really matter.
Okay.
So now having this property, I mean, we now have the power of turning like K insertion deletions into some constant times K insertion deletions. But we can do that like right at the moment that we receive the symbols. This is a good property and will be useful for proving something relatively important. Let's say we have our classic setting with Alice and Bob on the insertion deletion channel, and they want to communicate through this. What I'm claiming is that I can put two agents at the two ends of this insertion deletion channel, and then such that these two, Alice and Bob only deal with these two agents, do not see the insertion deletion channel, and then the whole thing is a simulated regular, like, symbol corruption channel. This is going to kind of directly imply the error correcting code result that we had, because you can first simulate the insertion deletion channel that you have with a regular channel and then apply your regular error correcting codes on that. But it's not going to be that good because we don't have that constant one here anymore. So what I'm going to tell you right now is that how these two agents are going to work. What they do is pretty simple. Let's CA just receives symbols from Alice and then attaches some synchronization symbol to that and sends it through the channel. On the other side, the receiver does the same thing that Bob was supposed to do in the previous slides. It tries to figure out what the actual index is using this I prime and the other indices that he has received so far, and then reveals M prime to Bob. And this way we can turn a insertion deletion channel with K errors into a regular channel with C times K corruptions. C times K errors. One more important thing here is that, well, so far we have always just attached the synchronization symbols into the messages that are being sent. And this is not, I mean, this requires the alphabet size to be larger than some particular number in terms of epsilon. My claim is that you can also do this simulation for binary channels. And so in binary channels, you cannot just simply attach a synchronization symbol to any bit that you send. So what we do is chopping off Alice's message into like blocks of some certain length. And then at the end of that block, we're going to send a binary coded synchronization symbol. I mean, you have a bunch of binary strings which are in a one-to-one correspondence with your alphabet of synchronization string. And you use those kind of strings at the end of the blocks of Alice's communication. And this would be, and this is kind of like sending the synchronization symbols along with the message. And I'm not going to get into the details, but one can show that using this, you can still simulate like insertion deletions with corruptions, even if your alphabet size is very small. So, yeah.
But how small is very small? Like, can you get down to binary channels?
Yeah. But well,
so you wanted the singleton down there, though.
You will lose the
Because of the
singleton one.
C
You will also lose this constant thing. This
Yeah.
constant will be like, yeah, but it's still going to be useful. Okay. Hopefully the last definition here. Well, now consider this new setup, which we'll refer to as the interactive communication. The interactive communication is yet another communication problem in which instead of Alice just sending messages, two parties take turns on sending different messages. Formally speaking, we assume that each of these guys has some sort of number or variable's value that he or she knows. And what they're going to do at the end of this communication is to figure out the result of some function with the inputs of x and y. To put it more clearly, you can think of the whole thing as two parties playing chess over a channel. X would be what Alice does for any possible configuration of the chessboard. Y would be the same thing for Bob. F of X and Y would be who is the winner. And probably the communication are going to be the game moves log. Like, what's the first Alice's move? What's the first Bob's move? So on and so forth. So we call this whole thing a protocol. Well, first let's assume that there are not going to be any errors in this channel. Like, you are playing chess, and it's guaranteed that anything that you send will arrive at the other side successfully. We will refer to this whole thing as a protocol of n rounds. The problem of interactive communication is the problem of finding a way so that for any protocol, any x, y, f, x, y, and communication in the middle, with n rounds that work on a channel with no errors, into a new protocol, which is P prime, with probably a larger number of rounds, that can tolerate some non-zero error rate. So if you let adversary does some sort of tampering with the messages that are going on, the new protocol has to be able to still let those two find out the value of x and y. So still in this setup, you can think of symbol corruptions or insertions and deletions. Just quickly, I should mention that insertions and deletions are not as trivial as they were in the one-way setup. Because, well, let's say adversary removes some message that Alice is trying to send to Bob. Then Bob would be waiting for a message, Alice would be waiting for a message, and the whole thing will stop. So we kind of force the adversary to insert one message after he removed one. The main point is that that channel simulation that we had is also going to work here for interactive communications. So what we can do here is to simulate the interactive channel that we have with insertion deletion errors with a interactive channel with simple regular corruption kind of errors, and then use the coding schemes for those regular errors to obtain codes for interactive communications where we have insertion deletion type of errors. And using, well, one of the famous kind of interactive coding schemes, we can find a code for binary insertion deletion interactive communication with these properties that can tolerate any constant fraction of errors up to 1/9, has a rate of 1 minus theta of square root of epsilon log 1/epsilon, and is efficient. And this is actually an improvement over the previous work in all these three aspects in terms of the maximal error that it can tolerate, having a rate which approaches to 1 as epsilon goes to 0, and being efficient. I'm going to skip this. And yeah, that's it. Any questions? Yep.
So, somewhere in your talk you mentioned that you use algorithmic LLM to do something. So, what does algorithmic LLM mean?
So, generally, I think it does. Well, it generates a random value for your random space, and then tries to find some bad event which happens, and then resamples all the variables that are not independent with that bad event, and does this repeatedly. And they